Today we're going to be talking about geometric translations, and we're looking at our note packet, and if you'd refer to page 136, these transformations that we're going to be studying are generally written in matrix form. And what we'll be doing is looking at how ordered pairs, how our typical points will be transformed. A translation is going to be a shift, a movement right and left, perhaps up, down. And the way we're writing this is in terms of a pre-image. A pre-image is a point that we would begin with. The image is the ordered pair that we are transformed to, the point that we are now ending with. So, this is the matrix form that I've written up here. It's a 2x1 matrix, x prime, y prime. The primes are always the ending point where we are being sent. The initial point, the beginning point, is called the pre-image. It's written in this 2x1 format as xy. And then we have hk. I think it's important for us to also see that we could write this in just a regular equation form without matrices at all. Look, in our array here, the top entries, x prime would equal x plus h. Y prime, our bottom entry, would equal y plus k. So h is going to be a number that we're adding or subtracting if it's negative to our pre-image x coordinate. Likewise, k is a number that we are adding or subtracting if it's negative to our pre-image y coordinate. So very, very quickly, let's just take a look at a couple of problems. This is on page 138 in our packet. It says interpret these equations. Now notice that they're writing the equations instead of in matrix form. We have x prime equals x plus 6, y prime equals y minus 3 as a translation. So the xy is where we start. The x prime, y prime would be where we end. And of course, you can imagine no matter what ordered pair you have, if you add 6 to it for that coordinate in the x direction, imagine that we had an x value of 7. Well, you add 6, all of a sudden you're at 13. You're 6 bigger. As we move to have bigger numbers on the x-axis, we're moving to the right. This would be 6 steps right. And likewise, if we look down below, y minus 3 is what we have over here for where we begin. This would be 3 steps down correspondingly. No matter what y coordinate we begin with, if we subtract 3, we're going to get smaller. And as we move smaller, of course, on that y-axis, we're moving down for those y coordinates. So this is really what we're seeing. Very similarly, in number 2, it's the exact same idea, except it's written in matrix form. You can see that we have xy plus the 2x1, 0, negative 3. There's no movement horizontally. If you add 0 to your x coordinate, you don't move at all, right or left. However, y plus negative 3, we will move 3 steps down. Okay, so from here, let's take a look at some of these other problems, and I'll try to scroll down just a little bit, maybe get a little more space. But as we look at, say, number 3, we have x squared plus y squared equals 1. And it's translated so that its center is at 1, 2. Find the new equation. Well, there are a couple of ways we could do it. Many students will find the correct answer without needing to do any of this matrix work whatsoever, because students will just remember the general equation of a circle is x minus h quantity squared plus y minus k quantity squared equals r squared. And certainly you can think of it that way and you'll get the correct answer. Very soon kids would say, well, that's x minus 1 quantity squared plus y minus 2 quantity squared. Here we have the same radius. Obviously, as we just shift a geometric figure right, left, up, or down, congruence is going to be preserved. Our image figure will be congruent to our pre-image. So I don't think it would be a stretch for us to know what the equation is immediately. However, if you would notice that you had a center of 0, 0, and you're moving 1, 2 to that new center, you can see that your new x position took your old and added 1. You took your new y position, took your pre-image y, and added 2. Well, notice what we could do very, very quickly. The author does this quite often. Solving for x and y. That's not very much of a stretch. We could just subtract a 1 from both sides in our top equation, subtract a 2 from both sides in our bottom, and now make substitutions into this original equation. Well, instead of having an x here, we'll have x prime minus 1 quantity squared plus y prime minus 2 quantity squared is equal to 1. Well, here's what we can do. We could certainly, once we have our image, our final geometric figure to where we've been moved, you can drop the primes. That's something that the author does quite frequently. And of course, what's the advantage to looking at the problem this way? Well, we might be dealing with more complicated shapes very, very soon. And in that regard, we might think, well, my goodness, how can we find a way to get this new equation of our image figure? And this is it. Take a look at number 4 very quickly. We need to complete the square. We've got y squared plus 2y. Well, take half of that linear term, you'll get 1. 1 squared is a 1, but you have to add a 1 to this right side simultaneously. We can see by factoring that we have a center at 0, -1. We also have a radius of 2. Remember, it would be 2 squared. But for number 4, they're saying translate this so that its center is at the point 2, 1. Well, again, we could immediately, knowing that our center is at 2, 1, and this is what so many kids want to do lightning fast, and they'll get the right answer. They'll say, look, I know I still have a radius of 2, but it's just being moved. Won't my new equation be x minus h quantity squared plus y minus k quantity squared equals r? This is my new center. Indeed, that's true. Absolutely. But could we write a matrix equation that would indicate what's happening? Well, look, if you'd go to a center, a new center at 2, 1, you could see that your old x coordinate, you added 2 to it. Your new y coordinate, you also added 2. Look, you went from -1 to 1. And just as we did before, we could solve for our x, solve for our y, and certainly we could make some substitutions here. And if you did, you'd see you get exactly this equation that common sense would seem to indicate. Okay, very fast, let's take a look at number 5. Very abstract problem, incredibly abstract problem. You're just given the general equation of a line, and you have x prime is equal to x plus h, y prime is equal to y plus k. Find this new equation of this line. This line's being moved. Well, look, x would be x prime minus h, solving for x. Y would be y prime minus k, and substitute those in. Look, you'd have a is equal to x prime minus h. This is why that new method is so important. Sometimes we can't just have a simplistic, super quick method of working with the center of a figure. Believe it or not, this right here would even be fine. We can drop the primes, and certainly we could then even distribute all the way across. It looks like we have something that looks like this. The C minus BK and minus AH, are all constants, and certainly we would expect to combine those like terms. But just grouping them over here, this is what we'd expect to see. Okay, so let's take a look at number 6. At number 6, it says two particles start at the origin and they move in straight lines with velocity v1 and v2 at different angles. Let me just look at the first movement here, v1. Here's theta 1. Obviously, we would be interested in finding the distance. Now, forgive me, I'm getting ahead of myself a little bit. Distance is always rate times time, and they're giving us a rate here of v1, but they're saying that we're traveling t seconds. So really the distance this particle will travel is v1t. With trig, if I find x and y via SOHCAHTOA, it wouldn't be too much of a stretch. Let's just realize that the cosine of theta 1 would be x over vt, v1t, and the sine of theta 1 is equal to y all over v1t. Well, what are we really seeing here? We're seeing this much, that x would equal cosine of theta 1 times vt. So let's put v1t in front. And this we're going to be able to do for our other particle as well. But look at this, very, very, very fast. We have the distance that's traveled for x and for y. Now, what this is really meaning is that, for our first equation, I'm going to call it x prime for our first image, we've got v1t cosine of theta 1. This is how much we move to the right, and y prime is going to be v1t sine of theta 1. Well, let's say that we have a second particle. Tell you what, I'm going to call it double prime just so that we have something to speak of. Obviously, it's a different velocity, it's a different angle, but it's exactly the same setup. The only difference is your velocity very well could be greater or less, and our angles are going to be different. So you'd say, well, what would my new x and y positions be for this particle 1 and particle 2? Well, we have this. They're saying, hey, how far apart are these? Well, wow, we'd need the distance formula, wouldn't we? Very, very, very fast. We'd need x2 minus x1 quantity squared plus y2 minus y1 quantity squared. And what would that look like? Well, just put it all in there. x2, we'd have v2t cosine of theta 2 minus v1t cosine of theta 1. Square it. And then plus, over here we have v2t sine of theta 2 minus v1t sine of theta 1. Square it. It's a square root all over it. So that's your distance. Tell you what, for number 7, I'm going to let you think about that a little bit. I'm going to get you the answer. But here's a huge hint. X prime is really going to be x. We're going to be moving along a line, y equals x. Y equals x has an angle of 45 degrees. What we just did a moment ago hopefully is going to definitely come into play. We've got our old x position plus this change. Remember, this would be like our velocity. Here's y prime is y plus t sine of 45 degrees. Check that out. Hopefully you can